Hawkeye Lunch and Learn. My name is Linda Snetzelaar, and I'm a professor in the College of Public Health at the University of Iowa, and I'm also Associate Professor of Outreach and Engagement. And so every month we're trying to showcase faculty from our campus here in the Des Moines area, in the center we have here. And I'm going to do one little housekeeping thing. If you could turn your cell phones off, that would be great. And I'll march right into a introduction for our distinguished presenter today. Dr. Don Gurnett is the James Allen and R.J. Carver Professor of Physics in the Department of Physics and Astronomy at the University of Iowa. And he's been on the faculty there since 1965. He began his career in 1958 working on the design of spacecraft electronics and worked very closely with Jim Allen and Jim Allen's Cosmic Ray Research Group. He specializes in experimental space research and has participated in more than 30 spacecraft projects. He has received numerous awards for research and teaching, including the very prestigious 1994 Iowa Board of Regents Award for Faculty Excellence. He was elected as a member of the National Academy of Sciences, also an incredible honor. And in 2004, he was elected a member of the American Academy of Arts and Sciences. He has co-authored and authored over 600 scientific papers and has done a great deal of work with students on our campus who are now in prominent positions in space physics research. So with that, will you please welcome Dr. Don Gurnett.
Thank you very much. Actually, it's really been interesting just talking to people before you came into the room. I've discovered there are several people around here that worked in the physics department on spacecraft projects at the same time. I think you ran our UNIVAC computer back in the 1960s. So my talk is kind of a reminiscence of the early part of the space program. Actually, the focus of my talk is really going to be on Voyager, which recently reached the interstellar medium, and I'll tell you a bit about that. But what I really want to do is kind of go through a little bit of nostalgia about the beginnings of the space program, which, as I hope you all know, began at the University of Iowa. So I'm going to relate some of my memories of that era. If you go to the next, 1957, in my mind, is a famous year. First, I arrived at the University of Iowa in 1957, about September 20th. During my high school career, I flew model airplanes, radio-controlled model airplanes, with tubes, and did that with some colleagues at Collins Radio. I also, in my high school career, built rockets with saltpeter, charcoal, and sulfur. It was a crazy thing to do. I remember the druggist in Cedar Rapids, I would come in and buy these cans of saltpeter, and he said, "Son, what are you doing with that?" And I said, "I'm making rockets." And he said, "Have fun." Something like that. So I was already primed for determined. So I arrived about September 20th, and less than 2 weeks later, Sputnik 1 was launched, picture of which is shown here. And those of you that lived through that era, and I don't know how many people were alive here in 1957, a fair number, but not all, which is the reason I'm going to kind of go through that era just quickly. Sputnik had a tremendous impact on the country because this was in the middle of the Cold War, and we had a Russian object flying overhead. And not only that, having achieved this feat of putting a spacecraft in orbit around the Earth was something the U.S. hadn't done, and you could even say at that time possibly could have been done. And it started a very strong trend to educate engineers in this country. In fact, our building there, I'm sure, was built with federal funds and was part of the whole era to try to catch up with the Russians. Anybody that lived through that era knows that that's what. Launched on October 4th, 1957. It weighed 183 pounds. You know, that's quite heavy in those days, and you'll see shortly what I really mean by that. Go to the next slide. Well, the U.S. response was called Project Vanguard. Anybody remember that? Put up your hands. I'm just curious. A few, not many. It was a Navy project, and it was actually a scientific satellite. That's kind of an important point, because at the time Eisenhower was president, and he was reluctant to launch a satellite because it might be threatening to the Soviet Union. And Wernher von Braun was pushing to launch a satellite, but Eisenhower specifically forbid him from doing that. Von Braun being, as you probably know, rocket scientist from Germany. Well, the satellite for Vanguard satellite weighed 3 pounds, and it had a diameter about a little bit bigger than a grapefruit. So I get a laugh right away. I appreciate that. You got the idea. We had this little puny satellite, and the Russians had already launched. Why don't you back up one slide if you'd do that? Not only did they launch a spacecraft, Sputnik 1, on October 4th, 1957, on November 3rd, they launched a spacecraft that weighed 1,120 pounds, and it had a dog by the name of Laika on it. Anybody remember that? Right. So not only could they launch a spacecraft 183 pounds, but they could go up to over 1,000 pounds, and we're trying to launch a 3-pound one. So, and I remember all this just very vividly. Go to the next slide. So here's the spacecraft, and here's the Vanguard rocket. And if you go to the next slide, I can remember seeing this on television. Next slide, please. There was a launch of it's called the TV-3, Test Vehicle 3 launch on December 6, 1957. See, it's what was it, September or October? It's October, November, December. That's about 2 months after Sputnik 1. And some of you may remember this, so why don't you run the video. Oh, somebody thinks my microphone down.
Not really.
Listen now.
I was in college.
I always like that last comment, the exact cause is classified. This is number 3. Is that right? Okay. All right. So, this is the way it was back then. We'd try to launch a rocket and it would blow up. Then, go to the next slide. The next step in the U.S. space program was Explorer 1 and Jim Van Allen. And Wernher von Braun, while he was developing the Redstone Intermediate Range Ballistic Missile down at the Redstone Arsenal. And he had wanted to try to launch a satellite, but he was forbidden to by Eisenhower. But as soon as Sputnik 1 was launched, he was given the okay. In fact, he had a vehicle stored away, if you read the history on this, hidden down at the Redstone Arsenal, that he was just ready to do this. And it was a modification of the Redstone rocket. It was called Jupiter C.
Where was the Redstone Arsenal? What state?
Huntsville, Alabama. Sorry, I should have mentioned that perhaps. And he had worked with Van Allen on V2s, launches out in the desert after the war. Van Allen was studying cosmic rays, and we knew there was an altitude dependence of cosmic rays, so he's putting Geiger tubes on captured V2 rockets. So it was a fairly natural thing when they decided to go ahead with what's called Explorer 1 that they would select Van Allen to fly the Geiger tube. And the Geiger tube is located right in here. And the Jet Propulsion Laboratory at Pasadena, California, they built the transmitter and also the final stage rocket up here. And if you go to the slide and click on it, here's the launch. There's a night launch. And you can see the top, on the next frame, you can see the top stage rotating. See it rotating? It was on a spin table that was driven by a motor, and that's how they stabilized the spacecraft. A really simple system. The rocket went up like this, arced over until it was horizontal and burned out of fuel, the main stage, and then because it was spin stabilized just like a football, they fired the final stages. Let's go to the next slide. And here is a picture taken in the National Academy of Science building. They were optimistic. This was launched down at Cape Canaveral. They were optimistic it would work. And this is Bill Pickering from the Jet Propulsion Laboratory, Jim Van Allen, and Wernher von Braun holding up a mock-up of Explorer 1. And it was, as you know, successful, the first U.S. spacecraft. Now let's go to the next slide. And it was also created the first great discovery of the space age. Van Allen was studying cosmic rays, but when they launched the spacecraft, they discovered that there were certain times in the orbit where the Geiger tube would stop counting. And it was soon realized the reason it stopped counting was that there was such a high rate of intense radiation up there that it was saturating the Geiger tube. It took a while to actually discover that, but that is the story. And basically there were two radiation belts discovered, an inner belt and an outer belt. And the charged particles up there spiral around the magnetic field and bounce back and forth between the two hemispheres like that, seemingly forever. This was a complete, total surprise. Nobody expected these extremely energetic particles, both protons and electrons, to be trapped in the Earth's radiation belt. And that has been the subject of study even to this day, how these particles get energized and they create the aurora and various other phenomena like geomagnetic storms. Now, I was studying electrical engineering just across the street from the physics department, and with my background, as I tried to explain rockets, electronics, I went over and to see if I could get a job. And I didn't talk to Van Allen, but I talked to his secretary, Agnes McLaughlin, who I've now known for almost all my life. She died about 3 years ago. And she said, well, write down your qualifications. And I said, radio control electronics, meaning model airplane radio control. But I could give you lectures on that. I even help people fix those things in hobby shops and so forth. And about a month later, I got a offer from Van Allen to work in his group. So I started at age 18. Go to the next slide. Here's a picture of me working on a transmitter, actually, in 1958. Now, the first project I worked on was S46. That 46 does not stand for the 46th attempt to launch. It was proposal number 46, and it would have been probably about Explorer 7. Well, I had a rude introduction to space science because the rocket failed. It went in the Atlantic down there. Then I started working on a digital system, a data encoder for Explorer 12, and that was successfully launched. It took a couple of years. Some of these projects were very short-lived. And it was launched very successfully in 1961. And if you go to the next slide, and I'm a student, and in fact, most of the people working on these projects were undergraduates. In fact, I can hardly think of any that were either not a professor or an undergraduate, and most of the work was done by undergraduates like me. And I started working next on the first spacecraft ever built entirely. See, Explorer 1 was built in part by the Jet Propulsion Laboratory and in part by our department down there. And it was called Engine 1. I'm sorry about the name, but that's a name the Navy gave us. Van Allen wanted to call it Hawkeye, but they had a classified project or something called Hawkeye, so it was called Engine. And I designed the data system in Engine. It was, I believe, the first digital data system ever flown on a spacecraft. Prior to that, the explorers all they transmitted tones that were proportional to, say, a voltage that was measuring. Not really bit, it's called analog. And so I designed a digital data system here for this spacecraft, you know, data zeros and ones with binary counters and turned into a shift register. I had some fairly unique things that were later issue of a patent. It was launched on, we took just about a year to build it. And I can remember coming home to sleep when the robins are waking up in the morning. I mean, it was just an intense effort to catch up with the Russians. It went in a polar orbit. Then we, right after that was launched, we started on Engine 2. By then, I am the project engineer in charge of the entire spacecraft, not the science part, but the engineering part. It went in the ocean. I watched it go in the ocean down there. The rocket, went, the flight before ours crashed in Cuba and killed a cow and caused an international incident. And so our flight had to be deviated slightly to the east so we didn't go over Cuba. But nonetheless, night launch, and I can remember the rocket going up, and I was in the tracking building there where they did the Doppler tracking, and all of a sudden it was following the line just like that, and it just changed, and I went outside and I looked and I could see it blinking in the distance. That's because it's going end over end. And then I was also a project engineer on Engine 3. Picture there, I'll show you that shortly because it changed my life. Engine 4, I was at Stanford University, and shortly after that I was hired back that was launched in '64, and yeah, I was hired as a professor in 1965. And then, now you'll see up there's an antenna on top of that. That's my antenna. I'll show you some things we do with that. Here's Engine 5. This is also an antenna, and that loop out there, kind of research I do, I'll explain in just a minute. And finally here we got NASA funding for this, and the name was changed to Hawkeye. And there's somebody here said they worked on Hawkeye. Who was it? There, okay. And I forget, what did you do on Hawkeye?
Magnetometer experiment.
Magnetometer, yeah, we had a magnetic field sensor out in the end of that boom that was the magnetometer. And I think you worked, you said you worked on the optical an optical sensor for determining attitude, which I hate to say failed, and I don't blame it on you, but those things happen. Now let me go back to Engine 5. Let me go to the next slide. All right, there's a picture. As I said, I was the project engineer in charge of it, still an undergraduate, and I heard a recording of what are called whistlers. They're signals detected on the ground. And I made a loop antenna here and a special receiver, took it out to my father's farm to test it. The reason we had to do that was that there's so much noise from 60 hertz power lines around the city, you can't operate it in the city. In fact, we took that out for the final test before we shipped it down to Cape Kennedy. This went in a polar orbit. These things right down here were to detect the aurora. And we made the first space measurements of aurora with this spacecraft. Now, okay, what's this loop antenna thing about? Well, I was interested in studying whistlers. You go to the next slide. And here's what a whistler is. There'll be a quiz afterward, by the way. If a lightning stroke occurs here, it sends a wave up into the ionosphere. That's this region of ionized gas. You've probably heard of the ionosphere before. And that wave, it turns out in that we call it plasma medium, it's an ionized gas. It more or less follows the Earth's magnetic field and interacts with the electrons here. And it just turns out that the high frequencies travel faster than the low frequencies. And of course, a lightning stroke is in an instant of time, and it emits this wave, and the high frequencies go faster than low frequencies. So in the other hemisphere here, over here, you'll hear a whistling tone, sort of goes like that. Now I'm going to play here, and I have to tell you, when Engine 3 was launched, I can remember the first time we commanded it on in Iowa City, And we not only heard whistlers, we heard all kinds of space sounds that had never been heard before. Let's play the recording of a whistler. These are known to be, click on that button. Flying over a thunderstorm, and each of those whistling tones is produced by lightning. I am not going to talk about this, but we also, for the first, one of our achievements at Iowa was discovering that there was lightning on Jupiter, and that's when the Voyager spacecraft flew by Jupiter. We heard whistlers, and we knew that there was lightning at that planet. Let's go to the next slide. Now, there's another phenomena called dawn chorus. That's what we call it nowadays. And this is a spontaneous emission from the radiation belt. The electrons in the radiation belt just spontaneously get together and make whistling noises. This is really pretty strange. You really don't expect up in the corner of the room the molecules to get together and whistle at you, but they do. And I'm going to, and the reason it's called dawn chorus, anybody know what that, ever heard of that term? Probably not, unless you're British. Because if you're British, you would say when the birds wake up in the morning and start singing, that's called the dawn chorus. And if you'll play it now, you click on the, yeah. Kind of a musical sound coming out of the radiation belt. There have been various people in the music world have been come to my office and listen to these things. Some of you may know there was the Kronos Quartet produced a performance called Sun Rings, which is played all over the world, and I used to go to pre-concert performances for it just to tell them the science behind it. It turns out these waves limit the length of time that a particle can be trapped in the radiation belt. They're actually quite important from a science point of view. If you want to know more about it, you can come take my plasma physics course next year. Starts in late August, and come learn about, you should have a little bit of algebra probably, and maybe even a little bit of calculus. Okay, let's go on to the next slide. Now, I sort of relayed here our history of building satellites, Earth orbiting satellites. I think we built a total of 8. There are a couple others I didn't mention there. And then we got into, as the space program started advancing in this country, we finally began to set our sights on the planets. Now, it was actually the Russians that first beat us to a flyby of Venus. But we finally reached Venus with Mariner 2. Went to Venus. That was in 1962. Notice how rapidly things are developing here. I started in 1958. 5 years later, we're sending instruments to other planets. Also, Mariner 4. You may notice the numbering system back then. Mariner 1 failed, Mariner 2 worked, Mariner 3 failed, and Mariner 4. Now they don't include the numbers of failures. We just label them after they've been launched. In those days, the failure rate was nearly 50%. You know, if you launch a spacecraft, but that's fortunately gotten much better. Now, neither of these planets, Venus or Mars, has a strong magnetic field. That was discovered with these spacecraft, and therefore no radiation belt. Now, at that time, it was known that Jupiter probably had a radiation belt. The reason is we could detect strong radio emissions coming from Jupiter up around 10 to 40 megahertz. And the inference was that Jupiter had a radiation belt. So immediately there was a push to try to study these outer planets, Jupiter, Saturn, Uranus, and Neptune. And if you go to the next slide, there are some people out at the Jet Propulsion Laboratory that realized that in 1977, with a single spacecraft, we could fly by all of these so-called outer planets, Jupiter, Saturn, Uranus, and Neptune. And there was a commission formed, chaired by James A. Van Allen, that studied this possibility. Now what you have to remember is the Earth goes around the Sun once every year. Jupiter goes around every 5 years, and so forth. All these outer planets go around very slowly, and I've honestly forgotten Neptune. It's up in the 200 years, almost 200 years. So you get this specific alignment only once every 179 years. And we could do this mission if it was launched in the period around August, September 1977. This was proposed to Congress under the name the Grand Tour, and Congress turned it down. Too expensive. So the Jet Propulsion Laboratory, who analyzed how much it cost to do the mission and so forth, they renamed the mission. It wasn't called Voyager then, by the way. It was called Mariner, after the sequence of Mariner. And they decided to call it the Mariner Jupiter-Saturn mission. And Congress funded it to go to Saturn. And then there was a period where they sent out proposals for who could fly instruments on it and so forth. And finally, I won one of those proposals. Let me make another point, though. In flying by Jupiter, you can use the gravity to increase the velocity of the spacecraft. And kind of the way that works, if this is Jupiter and you fly in behind Jupiter, the gravity pulls on the spacecraft and gives it a slingshot effect that just about doubles the speed. And then you can do it again at Saturn, same thing, a little bit less so at Uranus, and a little bit, not very much, at Neptune. This allows us to cut down the flight time to Neptune to 12 years instead of 30 years. We got to Neptune in 1989. It would take 30 years to get out to Neptune, even with our best rocket today. I mean, it's just orbital dynamics and how fast you can get a spacecraft moving. In fact, after leaving Neptune here, we're moving at 36,000 miles an hour now. You have to stop and think about that. That is really fast. A rocket, just to get it into orbit, takes 18,000 miles an hour. And really, it's about all we can do to get significantly above 18,000 miles an hour with a direct rocket flight. So it not only takes advantage of the lineup of all four of these planets, but also the gravity assist allows us to get there in a normal scientific lifetime, or I mean like 12 years instead of 30. So let's go to the next slide. Here's a picture of the spacecraft as flown. Here's a human being down here, so you get kind of a size. And this is in the assembly building down at what was now called Cape Kennedy. And so you get an idea of the size. This is the high gain antenna. That's for beaming the radio signal back to the Earth. And somewhere that's 11.6 meters, feet in diameter. Now, it was the first spacecraft that I had anything to do with that had a computer on board. I mean, this is just getting in the era where we could do things like that, with transistors, not tubes like I worked in high school. And it had a computer on board with 68 kilobits of memory, kilobytes, I guess it is. I honestly forgot that little detail. Now, that's not much. Your cell phone has a lot more than that, and any little hand calculator is vastly more than that. But that's what we had to work with Voyager, and it was very important because we could reprogram things. We could program the pointing of the camera. The camera is located right here. It's on a boom, and after launch, it folds out like this. That boom is not whole. We can't take a picture of the whole spacecraft assembled in its final form on Earth because the boom is not strong enough to hold up the camera. See, it's only out once we launch it that we can do that. So the camera system down here. Now, when you go so far from the sun, you can't use solar cells really anymore because, for example, I have to compute this. When you go out to Neptune, the sunlight is only 1/1000th of the brightness that it is at Earth. It just looks like a bright star. So we had to use a different form of energy, namely it's a plutonium power supply. Where do I have that here? Electrical power, plutonium-238, generated 470 watts. And so it's a radioactive power supply. What it does, it heats a thermocouple, generates a voltage across a thermocouple. A thermocouple is just two dissimilar metals, and if you have a temperature gradient across two dissimilar metals, it generates a voltage, which is how it works. We started out with 470 watts, and we're now down to 260. Plutonium has a half-life of 87 years, and so it's gradually going down in terms of power. And that will be the ultimate limit to our mission. We transmit at Jupiter. We could transmit 115 kilobits per second. That's now down to 40. I'll talk about that later. So what else should I say? There's 10 instruments. Transmitter power was 22 watts. My gosh, with our radio control model transmitters, it was almost that much. But nonetheless, we can get the signal back. So let's go to the next slide. Okay, now here's the Iowa instrument that we built in our laboratory. These are our antennas. They're 30 feet long. They're a beryllium copper antenna that's preformed to roll up in a tube, and we flatten it out, roll it up on a roller, and we have an electric motor there that drives the thing out, and so you end up with a kind of a stiff rod. They were originally developed in World War II as tank antennas. De Havilland makes them, and we worked with them to develop the antennas. Our receiver, I'll call it a radio receiver, is down in this, right down there. There's a picture of it. Weighed 1.4 kilograms and takes a little over a watt, 1.1, and here's kind of a drawing of stuff under there. And there are 10 other instruments, and I won't go through those here. Okay, let's go on to the next slide. So here was the launch. Voyager, now notice that Voyager 2 was launched on August 20th, and Voyager 1 was launched on September 5th. You might wonder why we did that. Well, it turned out just because of the position of the Earth and the time window in which we had to launch, that the first spacecraft to be launched had a slower trajectory to Jupiter. So Voyager 1, which was launched later, passed Voyager 2 on the way to Jupiter. So we named them in the order that they'll get to Jupiter. And I have to tell you, it's a great thing to watch these launches. It was a Titan 3C Centaur, and that was the highest performance vehicle we had at that time. Actually, the Saturn V, you could say, is a higher performance. It can get a bigger weight into a low altitude orbit. But the Centaur upper stage was a special liquid oxygen, liquid hydrogen stage that could get us up to very high velocity and got us to Jupiter in a little over a year and a half. Let's go to the next slide. Now, these are the trajectories that actually flown. I don't know if I like this drawing, but anyway, I'll explain it here. Now, only Voyager 2, here's Voyager 2. It was launched on 5th of September. Let's see, I hope I got that. No, I have that wrong here. Yeah, here's Voyager 2. It was launched on the 20th of August, and it went to Jupiter, Saturn, Uranus, and Neptune. So it's actually Voyager 2 that went to all 4 of the outer planets. Now, Voyager 1 went to Jupiter and Saturn, and at Saturn, a very crucial decision was made not to go on to Uranus and Neptune. And let me explain what that was all about. At Saturn, there's a moon, a very large moon called Titan. It's about the size of the planet Mercury. And there was evidence that it had a methane atmosphere, natural gas, or at least methane there. We didn't know what else. And Carl Sagan argued very strongly that perhaps there was a greenhouse effect, and I'm sure you all know what greenhouse effect is. I hope you do. There's discussion about greenhouse effect here on Earth, of course. He argued that there might be a greenhouse effect, and even though it's so far from the sun, there might be the temperature in that atmosphere on that moon might be high enough for life to exist. And I'll come back and talk about that. So once we flew by Saturn in such a way that we could go by Titan, we could not go to Uranus and Neptune. That's the bottom line. So that's the trajectory we ended up flying. Now let's go to the next slide. I forget what's coming next here. So we made the first close-up pictures of the outer planets. And these are the pictures. I'm not going to spend much time on it because I just can't here. But close-up picture of Jupiter with its red spot, a huge hurricane in the atmosphere. The clouds, the white clouds are ammonia clouds. Ammonia plays a similar role to water in our atmosphere. And you can see these bands which are moving around like jet streams. Picture of Saturn and its rings. Uranus is rather unphotogenic. You can hardly see anything, just a big kind of blue ball. Again, mostly hydrogen. Incidentally, these are all big gas planets. They're not like our planet at all. You can't walk on them. There's no hard surface. If you go down in through the surface, it's mostly hydrogen, gets more and more dense until you think it's liquid hydrogen. And then Neptune. Neptune had a hurricane in it over here. And so we had these great pictures, and actually when we came in closer, you can get much better pictures than this even, but I'm just kind of telling you what we did. Now we also made the first close-up pictures of the moons of these giant planets, and you go to the next slide. And here's a family portrait of all the big moons at Jupiter, called Io, Europa, Ganymede, and Callisto. I might say these are very famous moons because in the years 1610, Galileo looked through a telescope and he saw these 4 moons going around Jupiter, and he said Copernicus is right. The planets are going around the sun, for which he had a rather hard time being tried by a Roman Inquisition for teaching the heretical view that the planets go around the sun, and he was committed to house arrest until he died. I'll show you better pictures of these. These are just kind of give you an overview. Saturn has a lot of moons. There's Titan. I told you it was these are pretty much relative size too. Titan has this much bigger than our moon. And interesting, you can't see anything. You can't see any surface features. It's covered with, we like to joke, Los Angeles smog. You can't and it has a dense atmosphere. Actually, it has a dense nitrogen atmosphere. The only object in our solar system other than Earth that has a nitrogen atmosphere. You know, our atmosphere is mostly nitrogen. The oxygen has almost certainly developed because of plant life. So it was, I mean, that's pretty amazing. Out of the whole solar system, you have 2 objects that have a nitrogen atmosphere. How can it be like that? We're still puzzled over things. Every moon and planet just seems to be totally different. I would tell you that these are just accidents of nature, how the whole system formed and what the history was. Uranus has a series of moons here, which not very good pictures. Neptune has really 2 big moons. Now let me show you now. I know these pictures aren't very good, but I wanted to get them all on one slide. Now, actually, Saturn has over 30 moons, but there are a lot of little rocks, you know, that we call moons. These are the big ones. So I'm going to show you some close-ups of just a few of these moons, the ones that are most, I would say, interesting. Don't tell that to my colleagues. There's people that specialize in just one moon. They wouldn't like to hear that. Let me talk about Io. Go to the next slide. Here's a picture of Jupiter's moon, Io. And I'll have to tell you, this is a memorable event in my life because we're watching the data come in at the Jet Propulsion Laboratory, and we're closing in on Io, and we made a very close flyby of Io. And ever since 1610, all you knew about this moon was as a little dot of light. Just like you can take a home telescope and look at Jupiter and you can see these moons going around. So just overnight, we close in and we get these tremendous pictures of the moon. I mean, that's being right there at the point of discovery. And we received this absolutely incredible picture. It was joked that it was the pizza theory of Io. Looked like a pizza. Does that look like a pizza to you? Yeah, it does. And then there was a woman on the navigation team. Let me tell you, navigation, one of my risks here is I'll talk too much. One of the big things about closing in on these moons, we didn't know the orbit of the moon well enough from Earth observations. And so during the approach to Jupiter, we had to take pictures of these moons much farther away than this and compare them with star backgrounds like that star right there in order to improve not only our navigation, but also the ephemeris of the moon so that we could do some small thrusting maneuvers to bring us in on the right trajectory so we, A, wouldn't hit the moon, and B, would fly close to it. That's the name of the game. Now this woman, Morabito is her name, her job was to overexpose the edge of the moon and compare it with the star background and measure that distance there in an angle. And she looked at one of those pictures and she saw this thing sticking up out of the moon by about 60 miles. That's no little thing there. And it was immediately recognized that it's a volcano. And this moon has volcanoes all over it. These dark spots are active volcanoes. And you can see the material coming back on the surface, coating the surface. You see that white ring around there? That is sulfur dioxide snow. So there's a lot of sulfur in volcanoes. If you've been out to Hawaii, you'll know that. And this stuff comes out, it kind of precipitates in space and comes down and coats the surface and makes white sulfur dioxide snow ring around it. This moon is almost completely molten. And that's because the next moon farther out produces a tidal torque on it, just like our moon produces tides on Earth, and it flexes the moon and it keeps the moon completely molten. In fact, it's molten so close to the surface that even in a few years, which we've actually studied with the Galileo spacecraft, this whole picture changes. And that's because the volcanic material comes down, coats the surface, sinks into the surface, and gets remelted. So it's completely replating itself on a time scale of years. I would like to say that this is probably something like what the Earth looked like in the very early stages of formation of the Earth, where it was completely molten and, you know, having vents coming out and things like that. Okay, next slide. Now here's Saturn's moon Titan. Here's a Voyager image of Titan. You can't see anything on the surface. But it turns out it has a nitrogen atmosphere, and the pressure at the surface is 1.5 times the pressure on the Earth's surface. So it has a very dense nitrogen atmosphere, more dense than the Earth by 50%. Furthermore, there was an instrument on there that did infrared measurements. Rudy Hanel was the principal investigator's name, and he came back with the astonishing result that the atmosphere is just full of hydrocarbons. I'll just read some of them. I'll have to come up closer, I won't be able to read it. There's methane, acetylene, ethane. I can't read all of these, unfortunately, the picture is not good enough. Hydrogen cyanide and nitrogen. And furthermore, they were able to measure the temperature as a function of height by radio occultation. The radio signal from the spacecraft went, as we went behind the moon, the radio signal has to go through the atmosphere, and from that you can work out the temperature from the time delay in the radio signal. And this is the temperature, and that is in degrees Kelvin. That is 50 and 100 degrees Kelvin. Now you may not be familiar with the Kelvin scale. That's zero is absolute zero. And we're at 200, let's see, water boils at 273 degrees Kelvin. So that's very, very cold, about minus 400 Fahrenheit. Now, when they put on the precipitation, the pressure, temperature characteristics of these different hydrocarbons, and this is the actual temperature profile in the atmosphere, it predicts that that hydrocarbon will precipitate out at that point, forming rain, but not water rain. And in fact, if you other data we have showing close-up pictures here, you can see haze layers in the atmosphere, and these are these different hydrocarbons precipitating out. And we guessed after, and here, let's see, here's the characteristic line of nitrogen, and there's methane. So we expected that the methane in the atmosphere could very well be raining liquid methane. We thought that from the Voyager data. Now we've had another spacecraft now. How many of you heard of Cassini? I don't know if you have or not. If you haven't, go type Cassini into Google and go look at our pictures. Cassini has a radar, special radar that can see through that Los Angeles smog. And they've been able to map the surface, and we now know that there are hydrocarbon lakes on Titan. This is one of them. This is actually a radar image. In fact, there are lakes on Titan that are bigger than the Great Lakes, filled with hydrocarbons, probably ethane, propane. If you need energy, we ought to figure out how to get it back, but that's not an easy task. There's a tremendous amount of hydrocarbons there. Now, I always make the little joke that if you want to go drive your motorboat around on this lake, you're lacking a one ingredient. You got plenty of fuel, but there's no oxygen. This atmosphere has no oxygen. It's a so-called oxygen-free atmosphere that probably existed on Earth before plant life formed. So, Titan. Last picture, next slide, last moon I'm going to show you is Neptune's moon Triton. At Neptune, this moon Triton, and well, I don't have a lot to say about this. It's called cantaloupe terrain. Can you see the analogy? There's something different about this hemisphere down here. Looks totally different, and you can see these black sponges. These, we believe, are like geysers, but we don't know. It's not geyser. It's not water geysers because the temperature is minus 400 Fahrenheit. It can't possibly be water. People are trying to, it might be a nitrogen geyser, we aren't sure, that carries up some dark material. I'd like to tell you about all the other moons. They all have really cool stories like this. Maybe not all of them, but many of them. But let me go on now. And I'm going to show you the last picture that was taken by the camera. Now turn the power off on the camera. This was taken after the Neptune flyby, and we call it the picture of the century. It was taken on February 14th, 1990. And I know it's not a very good picture, but it's the whole idea of this thing. These are the pictures of the various planets. We could not see Pluto, and I think we do not have Mercury. Mercury's too close to the sun. But here's a picture of Jupiter. See, that's that frame there blowing up. Picture of Earth somewhere in here. I think it's right in there. That's the sun. Venus, Jupiter, and let's see, I'm having trouble with my own eyes here. Uranus and Neptune. So this was shortly after the Neptune flyby. It's the concept. We have left the solar system, and it's like looking in the rearview mirror of your car, and our solar system is behind us. Now, after the Neptune flyby, the project was, incidentally, we had several names for this project. First it was Mariner, Jupiter, Saturn. Then after we went by Saturn, guess what? We went to Congress and we asked for funding for the Neptune, Uranus, then Voyager, we changed the name. Voyager, Uranus, Neptune mission. Now after Neptune, it was renamed again and we asked for more money, and it's renamed the Voyager Interstellar mission. Now, what I want to do is finish the lecture by saying, why do we call it the Voyager Interstellar mission? And this is going to be a little more scientific oriented and a little less pictures. If you go to the next slide, let me start out with a totally different subject, and that is the solar wind. How many here have heard of the solar wind? I'm just kind of curious. Oh, lots, a lot more than some of the other topics I asked you about. The sun is very hot, and there's a gas escaping from the sun all the time. It's called the solar wind. And you can even see it in this picture. You can kind of get an idea that that's happening. These are actually magnetic fields around the sun, but they look like they're being stretched out. And there is this wind flowing out from the sun. It's actually a plasma, an ionized gas, consisting of mostly protons. That's helium or hydrogen plus, and a little bit of helium and a few other elements. And it flows by the Earth at 1 million miles an hour, 400 kilometers per second, about a very high speed. It's a supersonic wind. It's moving faster than the speed of sound. And you may know, you hear of magnetic storms. It causes various effects on the Earth. For example, magnetic storms. If you've ever been up in Alaska, you can see the aurora going around in the sky. The aurora is driven by the interaction with the solar wind. So there's this gas coming out from the sun we call the solar wind. If you go to the next slide, so as soon as it was discovered back in the about 1959, I think it was, people started asking the question, well, actually we knew it even before that, in 55. That was based on comet observation that we we're almost certain there was a wind there. So the question was asked, where does the solar wind end? You know how scientists are, they got always asking these questions. It's coming out from the sun, does it ever stop out there? Well, you might ask, why would it stop? Well, the reason is, and forget the equations here, as the solar wind expands out from the sun, it's essentially expanding into a vacuum, so to speak, into a bigger and bigger volume. So the density goes down. It just steadily goes down as that solar plasma goes out from the sun. And at some point out there, it was postulated that the pressure of that solar wind will match the pressure of the gas between the stars. We sometimes call that the interstellar medium. So you may think of space as a vacuum, but it's not. There's still material out there. You should be glad of that, because that's where the Earth and the Sun were made from, that interstellar plasma. That's where it came from at the formation of the solar system. But the catch was, we didn't know what the density of the interstellar medium is. Despite these numbers here, frankly, they just didn't know. There's no good way to measure it. And so that was now the objective to both Voyagers are moving out from the sun. Voyager 1 is moving at 3.5 astronomical units per year. An astronomical unit is distance from the sun to the Earth. That's kind of a basic length scale that we use. And so we're going out farther and farther. Now, let's go to the next slide. Turns out the sun is moving relative to the nearby stars and that interstellar gas. And so it isn't just a spherical, like a bubble that the solar wind makes, but because the sun is moving with respect to the interstellar medium, we expected there would be a bullet-shaped boundary between the solar wind and the interstellar gas. And if you look at it in the sun's frame of reference, the interstellar gas is approaching us. And strangely enough, we actually know that number. It's like 23 to 26 kilometers per second. I could go into how we know that. We've known that for a long time. Now, so it just turns out that Voyager 1 and 2 are moving out in this direction toward the nose of what we call the heliopause. We postulated that there was a boundary called the heliopause between the solar wind, this region here, which we call the heliosphere, and the interstellar plasma. So the idea was, can we reach this boundary and get into the pristine interstellar gas, the interstellar plasma? Now, how far out did we think that might be? Go to the next slide. Here's a list of various authors, published papers, most of them I know, making their estimate of how far out. Okay, in 1956, a guy by the name of Myers, he said 5 AU. Well, that's up where Jupiter is. Didn't turn out to be true. Here's another estimate, 45 to 90, 20. Here's a good friend of mine, Lou Lanzarotti and Michael Schultz in 1969, they said 5. They're still good friends. And then you'll notice if you just go down here, here's my name. 1993, I published a paper, and I'll show you how I got this number. 116 to 177 AU. Now at that time, in 1993, we were at about 40. And a lot of people didn't want to believe this number because it's so far out that it would take us 20 years to get there. And I hope you can imagine that if you propose to Congress to go another 20 years at several million a year, this was not viewed very favorably. Nonetheless, I stood my ground and I published that number, and I'm going to explain how I got it because it's actually quite simple. Let's go on to the next slide. Now, in the 1980s, 1983, we discovered a radio emission that we call the heliospheric radio emission. And so you remember I have an antenna on there and I can detect radio waves, and we detected a radio emission down at about 2 to 3.5 kilohertz. And why don't you play that now? Click on it. And this is 14 years from here to here. Rising tones, lasting about a year. There's one there. Several of them right here, very weak. And afraid we'll just have to let it run along there. This is frequency and time, and I think you get the idea. The cursor's moving along, showing where we're listening. And then in 1992, a big one. Now, since then, there have been other events going up to the current time, but all very weak. These are the best ones to listen to. Now, so the question is, what's causing this? Where do these radio emissions come from? Well, we thought maybe it might be coming from another stellar system, a pulsar or something like that. We thought it might be coming from one of the planets that we just didn't know it was doing that, you know? Doesn't do it all that often. So I came up with a theory. Let's go to the next slide. Now I'm going to have to talk about some other things here. Every now and then there's an explosion from the sun. And they're called coronal mass ejections, a huge explosion, solar flare on the sun. But let's play that now. You can see it. No sound. So these things go on at the sun, and when that blast comes out by the Earth, that's when we have a geomagnetic storm, and the aurora brightens up and so forth. Now I have to explain something else. Those events create a shock wave going out from the sun. That's what that is. We call it an interplanetary shock wave. It may not be perfectly circle like this. This we call a cartoon. This is kind of how we think it works. You probably know that we're bathed all the time in cosmic rays. If I were to set a Geiger tube out here, it would sit there and count. And there's particles going through our body all the time called cosmic rays. Now, when if that shock wave is out here, the shock wave is very turbulent and it prevents cosmic rays from entering. And we see a decrease in the cosmic ray intensity. This is the kind of thing that Jim Van Allen's liked to study. This is his favorite topic. And these are called Forbush decreases, after a guy by the name of Forbush Decrease that worked at Iowa at one time. And so when you see a Forbush decrease, that's really telling you there's one of these shock waves just went by you. Now let's go to the next slide. Here's what I discovered. Here's the cosmic ray intensity, and it varies with the solar cycle every 11 years. And here's a Forbush decrease. See, the cosmic ray intensity went way down. And here's another one. That's the biggest in recorded history, over something like 80 years of observations or so. What I noted was the radio emission occurred 412 days after this shock wave. In this case, it was 419 days. Well, you add up 2 and 2, and I said the radio emission is produced by a shock wave coming out from the sun. Now, we know the velocity of the shock wave. It's like 4 to 800 kilometers per second. We know it took 400 days. I postulated, go to the next slide, that the radio emission, here's the shock wave, the radio emission was produced when the shock wave interacted with the heliopause. So, compute the distance to the heliopause. 600 or 800 kilometers per second, 400 days, come out with the distance. That's how I got 116 to 177 AU. Well, I've told my colleagues in the last 20 years that every year goes by, my theory is better. And a few years ago, about 3 or 4 years ago, we got to 116 and we still hadn't gotten to the heliopause. So I'm now in range of my prediction, and a few more years went by. Now, let's go to the next slide and I'll show you what to expect. This is the density of the solar wind. It's over there. We measured it in particles per cubic centimeter. Now, I told you earlier, as the solar wind expands out from the sun, the density just goes down, 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 like that. And on this log plot, that's the solar wind getting less and less dense. And then at the shock wave, I forgot to tell you, the solar wind is supersonic. It has to go through a shock transition before you get to the heliopause. You take my fluid dynamics, that'll be 2 years from now before I teach that. But you have to go through a shock transition. You know, shock waves, if you didn't miss that, that's like an airplane moving at supersonic speed through the air, creates a shock wave. Then there should be a very big jump in the density. Now, why is that? That's my prediction. The solar wind is very hot. It's about 1 million degrees. You believe that? That's because the sun is really hot. The interstellar medium, we guessed, would be very cold, about 6,000 degrees. Still pretty hot, but a lot colder. To get pressure balance across the heliopause here, the pressure balance means the number density times the temperature has to equal number density times the temperature. So if the temperature went down, the density has to go up. It's just one of these reciprocal relations. And I predicted the density should be about 1/10 of a particle per cubic centimeter. And that it turns out the plasma frequency, an characteristic oscillation frequency in the plasma, which is responsible for those radio emissions, by the way, should be a couple 3 kilohertz. Go to the next slide. All right, finally, after a long wait, a really long wait, years, from 20 some years ago, we detected plasma oscillations in April to October. I had that wrong. It's April to May. I typed that wrong. 2013. And we detected plasma oscillations that shows that Voyager is in the interstellar plasma. And I'm going to play this now. The things you want to listen to, this is very weak. There's one case, and here's another case. So go ahead and play that. Here's a tone. Next one's going to be stronger right there. We detected this one first, then looking through the data in more detail, we found this back here. Incidentally, our data is stored on a tape recorder. You know, just an old-fashioned tape recorder, actually an expensive tape recorder designed to store the data. And that tape recorder has been running since launch. Not continuously. They record my data on it, and then every 3 months we play it back. Or 6 months sometimes, depends on how much we get stored on there. So thankfully, that tape recorder is still working. Let's go to the next slide. There was a considerable amount of, shall I say, consternation about whether I was right in my somewhat esoteric explanation, which I really didn't go into. After all, plasma oscillations, and take my plasma physics course next year, and I'll explain all about it. And finally, they had an inquisition. I will call it an inquisition. Not quite, but it was a 3 telephone conversations with all the other colleagues on Voyager, and I finally convinced my colleagues that yes, we are in the interstellar medium. There are some holdouts which you can read in the New York Times, but on September 12th, 2013, NASA officially announced that Voyager had reached interstellar space, and there was a lot of news coverage over that. I don't know if any of you saw it, but it was in the, New York Times front page, Washington Post, almost every paper in the country, seemingly, and Discover magazine, and so forth. So it was a really pretty big event, which is probably why I was invited to come here and talk. Is that the truth? So anyway, I don't know if I get the timeline about right.
That's for doing that. That's for doing that.
Yeah. Okay. Thank you. Thank you. Right. 36 years since launch. I should have said that. 36 years from launch. You want to know how far we are from the sun? Why don't you put the next slide on? Oops. I don't know. Next slide then. Okay, there we go. How far is Voyager from the sun? Well, it's 127 astronomical units. That's the distance between the sun and the Earth. 127 times as far out. 11 billion miles. I'm not much of a fan of using miles in this connection. Roughly 4 times as far as the planet Pluto. Here's the real zinger. It takes the radio signal 17.5 hours to reach the Earth. Now, I don't know if that rings a bell. Radio signals, light, travels really fast. It's 186,000 miles a second. When the astronauts, I don't know, some of you will remember this, when the astronauts landed on the moon and mission control would ask them a question, there's a noticeable time delay, about a second. It's the first time I think that a human can perceive of the time delay due to speed of light, just by normal senses. When you talk to somebody on the telephone, that goes at the speed of light, but if you call somebody in Los Angeles, you can't perceive it at all. So it's about a second to get to the moon, and this takes 17.5 hours. Astronomers like to talk about distance in light years. Have you ever heard of that? How far light goes in 1 year? It's a really long ways. Well, we're not out there a light year yet, but at 17 and a half hours, we're almost a light day. That's pretty impressive. So anyway, I just thought I'd tell you that. I should take time for questions at this point. Yes.
I heard your presentation maybe 8 or 9 years ago. You had launched something that's going to take 7 years to get to Saturn.
Oh yeah, that was Cassini. Yes, that was Cassini. Right. Yep, launched 1997, got to Saturn in 2004. And we used gravity assist. We flew to Earth, Venus, Jupiter, gravity assist to get to Saturn. That's how we used the gravity assist thing and it took us 7 years to get there. It's a really long ways out there to get there.
Once it got there, what happened?
Well, we put it in orbit around Saturn, and if you can just remember the word Cassini, you can put that in Google, and we have all of these great pictures of the rings and studies of that moon Titan and the hydrocarbon lakes, and it's really been a tremendous mission, still going on. We hope to run it another 3 years. Okay, yes.
Well, yeah, much of this and your calculations have to do with knowing how fast Voyager is going. So what were the methods you used to know its velocity, and can you measure a redshift on its signal?
Yeah, we can.
Oh, yeah.
We use a transmitter, and there's a Doppler because there's motion, so you just measure the Doppler shift. It's just that simple. It's more complicated to know exactly where Voyager's at. I could go into that, but you may not want to hear how long the story is. Okay.
Is there any more information that you can continue to get from Voyager?
Question is, what further information can we get from Voyager? Actually, if you can picture this, the heliopause is kind of a bullet-shaped object, and the interstellar plasma is now streaming around it, just like water would stream around the bow of a ship. So we aren't completely out in the pristine interstellar medium. We're in the medium, but for example, the magnetic field is being distorted. It's being distorted by the flow, and we want to find out the interstellar magnetic field strength and so forth. Let me go. Is that okay for? Yes.
Two questions. One is, could you give your thoughts on the funding of NASA and how that's changed over the years? And also, have you watched any of the new Cosmos?
I have not on the letter. I should, but I've been just hopelessly busy in the last several months, actually. Let me address the other question. Of course, you know probably that the United States does not have the capability of launching a human to the space station now. We pay the Russians to do that. So there is a big controversy going on now, which is how much we should spend on human spaceflight. Now, I am in the robotics world, with a couple exceptions. We flew on the shuttle. And I mean, Voyager is a robotic spacecraft. And I'm clearly an advocate of doing robotic exploration, like we landed on Mars with the Curiosity rover and so forth. There is a front page of Aviation Week about 2 years ago or so said the last fighter pilot has been born. Now, if you grasp the significance of that, we're spending a lot of money on drones. And recently, the Navy has autonomously launched an airplane from an aircraft carrier and had it all by itself come back and land on the aircraft carrier. It shows you what you can do with drones. So I think the future is probably in the robotic arena, because human spaceflight is exceedingly expensive. There is a lot of talk about, well, the first President Bush announced a national objective of landing on Mars. Now that I find, appealing. I think landing on the moon was a milestone in human history, just for having done it. And you can have a similar reaction if you want about Mars. But now, first President Bush, that must have been 15 years ago. He announced this
national objective. And the cost then was estimated to be $500 billion. My guess is in the current cost, it would probably be $1 trillion. And you surely must follow the national debt enough to know that that's almost a number we can't afford, seemingly at the present time. And so the human space program right now is in kind of a, well, they're flying things to the space station, but they don't really know what they're going to do next. I believe that's, yes.
Wonderful presentation. Can you give us your impressions at the time of the Cuban Missile Crisis? Just how you lived through that with Dr. Van Allen and others.
Yeah, I certainly remember it.
And then the other, do you have an opinion on whether we should really put on a political push to adopt the metric system at the grade school list level?
Boy, we almost have our lab.
Yeah, right.
Yeah. Well, that didn't happen. There was a push to do that 20 years ago. I don't remember when. But I think what kind of stopped that, they realized from a manufacturing point of view with CAD, CAM, computer-aided design, that you could just multiply by the right constant in the software that runs your milling machine and all that, and it became less important, I think. And I think that's probably still true. However, I don't have a strong opinion on that. I mean, it is true that if you have a European or Japanese automobile, it probably has metric screws in, and if it's American, it's British engineering, I guess they call it. But you can go down to the hardware store and buy both. So I guess my reaction is we're getting along okay. It's maybe inconvenient sometimes. What's your reaction?
Hard to say. I'm sorry, I'm a former elected official, and it's hard to tell people they should do something that you think they should do, but they don't want to do.
Yeah.
What about the Cuban Missile Crisis? Did you guys live through that in Iowa
The
City?
Cuban Missile Crisis. I certainly did. Yeah, I can remember it. I can remember it vividly. 1962, I would have still been in undergraduate. I was an undergraduate up to, so I just about graduated at that point, I think. And I remember it was a very scary thing. And hey, let me explain it this way. I used to, when I was an undergraduate working for Van Allen and so forth, travel to Washington, the Naval Research Lab and all that sort of stuff there. I used to just hope that the Russians didn't drop a bomb on Washington while I was there. I tell my kids that, and they just think Grandpa's going crazy. But that was the era. Some of you remember it? People were in brisk business in bomb shelters. Really true. So it was a good thing. And then, after the Soviet Union collapsed, there were then conferences between the U.S. and former Soviet Union officials. Do you remember reading that in the paper? And they exposed all the secret things and so forth. And it turned out, apparently, it was really close because the Russian commanders in Cuba had been authorized to use nuclear weapons had we attacked Cuba, which we did not. Let's see, the Cuban Missile, the invasion of Cuba by these 61. It was before that. So I don't know, that's what I know about it. I've had a lot of personal contacts with the Russians in that Soviet era too. I could have a whole story about that if you want. But
I've just been dying to ask the plasma physicist this question. What do you think the probability of our ever developing fusion generation?
Well, we should be spending a lot of money on it, I think, but we're not. That's one of my reactions. Let me explain to everybody. The question is, should we do about fusion? That's where you take two hydrogen atoms, combine them, and make helium, and there's a tremendous release of energy, and that's what happens in a hydrogen bomb. There's a lot of problems with that. You have to heat the gas up to 30 million degrees before the fusion reaction will occur. That's because the two hydrogen plus atoms have a mutual repulsion, and you have to slam them together hard enough to get over that called barrier. And of course, in a hydrogen bomb, it happens in a microsecond. We need to slow it down, right? by a lot. Now, you know, someday we're going to run out of oil. A lot of people don't like to hear about that statement, but it's true. I don't know if it's 50 years from now or 100 years from now, and that is the fusion is possible to produce a huge amount of energy. You know, you can get hydrogen from water. So will they achieve it? Well, the Princeton fusion test reactor about 10 years ago achieved break even. They have a magnetic bottle. See, here's the problem with fusion. You have to get to 30 million degrees, and if you're going to contain that in a box, let's say, you got two problems. One, the plasma. It's a plasma when it's heated up that much. It can't be a normal gas. First, it'll melt the box. And secondly, the box cools the plasma, and you can't get to 30 million degrees. So the approach has been to use a magnetic bottle, just like the Van Allen radiation belt. You remember I discussed that? The charged particles are trapped in the magnetic field. It's exactly the same concept. So you make the magnetic fields like they get them very strong here, and the particles will bounce back and forth here, you know, spiraling and bouncing back, just like they do in the radiation belt. So interesting, our kind of physics is actually bears on the attempts to achieve controlled fusion. Now there is a project called ITER, International, I can't explain just what those acronyms, but that's being built in France. But boy, it's been terribly slow coming because there's many national, you know, China I believe is a part, the U.S. is just a very minor part, but the French, the Japanese, and it took them 10 years to negotiate even where to build the thing. So I'd rather see a national effort rather than an international effort that's so full of politics. Yeah, right. So I'm all for it, but you know, it isn't clear you can achieve it. Yes.
Thank you all so much, and thank you, Dr. Gurnett.
You're welcome. You're welcome. All right.